Hey, it's Miss Adams from Flamingo Math. We're looking in Lesson 5 today, polynomial functions and complex zeros. You might recall from Algebra 2 the definition of a complex zero. You might recall from Algebra 2 how we defined a complex number as any number where there is both a real number part and an imaginary part. In this example, you can see that the square root of -1, if you remember, is defined as I. And we can simplify the principal square root for imaginary numbers using that definition. So the square root of 9 is 3, and the square root of -1 is defined to be I. So we have this complex number, 3i, for finding the square root of a negative number. So a complex number is any number in the form of a plus bi, where a is the real number part and bi is the imaginary part. The fundamental theorem of algebra tells us that if we use factoring, we can write any polynomial as a product of a coefficient and some linear factors, x minus 1, r sub 1, x minus r sub 2, x minus r sub n, where those r's are complex numbers. So we're not going to teach factoring too much, but we will review this concept with an example, x cubed minus 6x squared plus 13x. So what we want to do is we want to factor out the greatest common factor, which is x, and that's going to leave us x squared minus 6x plus 13. Now that quadratic, x squared minus 6x plus 13, is called relatively prime. It can't be factored as a product of linear factors. So in this case, we would need to use the quadratic formula in order to solve that polynomial. We're going to try the quadratic formula. So the quadratic formula first says we want to solve for x if we take the opposite of b. B is -6, so the opposite of b plus or minus the square root of b squared minus 4 times a is 1, and c is 13, all divided by 2 times a, which is 2 times 1. This becomes simplified 6 plus or minus the square root of -16 divided by 2, which is the square root of 16 is 4i. So 6 plus or minus 4i divided by 2. And each one of those terms we can divide out a 2. You can't divide unless you can divide by each of the terms in the numerator. So we can divide 2 into 6 and 2 into 4. Given us complex zeros at first 0 is going to be where this x is equal to 0. So at 0, and then 3 plus 2i and 3 minus 2i. Using the idea of the the fundamental theorem of algebra says that we can factor as linear factors. So factored form could be x, and then we're going to take these zeros, subtract 3 and subtract 2i, and then for these zeros, subtract 3 and add 2i. This is called factored form of that polynomial. If we factor this with two variables, our variables are x and y, we can take out a common factor of y. Then we have 4x squared plus 25. Now if we want to factor 4x squared plus 25 across complex numbers, then we want to isolate 4x squared equals -25, divide by 4, And to clear the square root, we want to take both the positive and negative square root of negative 25 over 4, which leaves us plus or minus 5i divided by 2. Now, factoring that in factored form, we've got the y as the greatest common factor, and then x minus 5 over 2i and x plus 5 over 2i. We're just simply taking this factor, x equals 5i over 2, and then subtracting if it was the positive, and then adding if it was the negative to get factored form. One more time, we're going to talk about even and odd multiplicity. If a polynomial function has a factor that's repeated, these duplicates are labeled as multiplicity of n. We saw that in the last lesson where the zeros occurred. If a function has a real zero at c, odd multiplicity, the graph of the function will cross the x-axis. We'll cross the x-axis at the point c0. If the function has a real zero with even multiplicity, the graph will be tangent to, or just touch, let's say be tangent to, or touch the x-axis at that ordered pair c0. For example 3, you want to use your calculator and sketch this graph. It should be as the image here on the notes, and you can tell by looking that here the graph is going to cross the x-axis, so that's odd multiplicity, and we're going to be tangent to the x-axis here. That's even multiplicity. And if you think about the factors, x plus 2 cubed is odd, so we're crossing at negative 2, 0. But the other factor, x minus 1 squared, is an even factor, power 2, and we're looking at a 0 of 1. So x equals negative 2 is said to have multiplicity 3, or odd, and x equals 1, that's 0, is said to have multiplicity 2, or even. In this example, we've got the graph of a polynomial, and based on that graph, what's the smallest degree of h of x? Well, it's got 1, 2, 3 terms, so the smallest degree is going to be 4. And then what else do we need to do? We want to use the knowledge that we have about zeros and other graphical behavior to talk about what we know. Well, we got zeros at negative 5, we've got a 0 at negative 2, and we've got a 0 at positive 2. Putting all of that together, the zeros at negative 5 and not exactly 2, but close to being 2, are odd because they cross the x-axis. But the 0 at negative 2, it's got to be even because it's tangent to the x-axis. So we have even multiplicity. Since it's tangent to the x-axis at negative 2, 0. We got the sum of the multiplicities. That's how we know the degree is 4, if we add the multiplicities of the zeros. Using the rule of 4 in example 5, they're giving us a graph. It looks like it's a third-degree graph, and we want to use what we know about the behavior of polynomials to see if we can write a possible equation. So in the rule of 4, can you take a graph and turn it into an algebraic expression based on what you know? So this graph is called y equals k of x, and we know that we've got to have some factors for the zeros. And where do those zeros occur? 1 is at -2, but it's even multiplicity, so we need another factor. And then we have an odd multiplicity at +3. So what would happen is we would have a leading coefficient, and if we add 2 to that x, then our factor is x plus 2. And if we add 2 to the other side, we have another x plus 2. And in this case, +3, we're going to subtract 3 and get a factor of x minus 3, because I'm thinking about those factors, turning them back into an equation with x plus 2 squared and then x minus 3. Now, what else do we know? We know that the y-intercept is at 0, 2. So if we use that idea that we've got a y-intercept at 0, 2, then we could plug in 0 for x and 2 for y. So this is my y value here, y, k of x is y, and say 2 is a times 0 plus 2 squared and 0 minus 3. I'm using that equation, substituting in the point that we know. So 2 is equal to 4 times -3 times an a. 4 times -3. So -12a is 2. Our a value is -1/6. That means we can put this entire thing together and say k of x is -1/6 times x plus 2 quantity squared and x minus 3. So we've taken knowledge about polynomials, an ordered pair that we could visually see, and we've written an equation that models the behavior of that polynomial function. That's called using the rule of 4. Another important fact from Algebra 2 was the conjugate root theorem. So the conjugate root theorem said if we have a polynomial with rational coefficients, then an irrational roots where the polynomial equals 0 occurs in conjugate pairs. That means if you have a plus the square root of b, if that's a solution, then its conjugate, a minus the square root of b, is also a root. They come in pairs. Likewise, if you have a complex 0, a plus bi, then a minus bi, that's its conjugate, is also a 0. In a polynomial function f that's odd degree with real coefficients is going to have at least one real 0. In example 6, a polynomial function f of degree 5 whose coefficients are real numbers has zeros at x equals 2, x equals 3i, and x equals 1 plus I. What are the remaining zeros? Well, this is a real 0, so it's by itself, but x equals -3i is its conjugate, and x equals 1 minus I is its conjugate. So those are the conjugate root theorem. It's these two that are missing. So we have 1, 2, 3, 4, 5 zeros in that case. For example 7, I've drawn the graph based on my previous work for this problem. We've got a polynomial, its degree is 4, so 4th degree, it's going to have that W shape to it. The real coefficients, the real numbers that have zeros are 2, 2, and negative 3 minus I. That tells me x minus 2 is a factor twice since there's a pair of them. And then we want to think x minus 3 minus I as another factor. And also we know that negative 3 minus I is the other zero, its conjugate pair to that. So thinking about turning this zero into a factor, we've got x plus 3 plus I. If you expand this binomial square, you're going to get x squared minus 4x plus 4. And just to save time, in this next piece, you've got x minus 3, quantity squared, and you've got minus I squared. So I grouped the x minus 3's together, this one, and then negative I times positive I is negative I squared. Expanding all of this becomes x squared minus 4x plus 4. And then this term is going to become x squared plus 6x plus 10. Now, College Board will not ask you to do this on their exam, but this is just a good Algebra 2 practice of things that you may or may not have seen in a previous course. I'm going to fill in these values because I've worked this out ahead of time. And we want to analyze the graph for some characteristics. So if you have access to a graphing calculator, you might want to enter into your graph window x to the fourth plus 2x cubed minus 10x squared minus 16x plus 40. So I got that by distributing this line right here. And if you want to analyze that using your calculator, I'll save this. You can do this later. We had a relative minimum value of 23.95, an absolute minimum value of 0, a relative maximum value of 45.86, and a y-intercept at 0.40, an x-intercept at 2, 0, an unbounded behavior to the left and to the right. And like I said, we won't be asked to do something that difficult on the AP exam. Now, you may need to be able to factor some basic things like this. And if you recall from Algebra 2, you could factor by grouping 2 at a time. Take out an x squared as your greatest common factor and end up with x minus 3 here. And then 1 would be your greatest common factor for the second two terms, x minus 3. If we set that equation equal to 0 so that we could find the zeros, y is 0, and you have x squared plus 1 as a factor. It was used distributive property with x minus 3. X squared plus 1, when is that factor 0? When x squared is negative 1. So taking the square root of both sides, that's plus or minus the square root of negative 1, which is a complex 0 of I. So we have 2 zeros that don't show up on the graph. And then the second factor, when is x minus 3 0? That occurs when x is positive 3. So if you want to factor f of x over the set of complex numbers, the factored form is going to look like x minus I, x plus I, and x minus 3. Those are our factors that we were asked to do. On number 9, you want to try that by yourself. It's similar, just has some different ideas, and you can come back and check your work against mine. If you factored by grouping, you took out an x squared in the first two terms, and you took out a 4 in the second two terms after you took out the 2. And then you had x squared plus 4 and 2x plus 5. Notice I divided the 2 into the 0 and got rid of that. X squared plus 4 gives me 2 complex zeros, 2i and negative 2i. And then the linear factor gives me a real 0 at negative 2.5. The linear factors look like this, and the zeros we wrote as a set. Then in our last example, if x equals 1 is a 0 of a function, how could we write f of x as a product of linear, irreducible quadratic factors, each with real coefficients? That means we're going to factor over the real numbers and reduce it down as far as possible. So what I did is I used the idea that x minus 1 is a 0 of 3x cubed minus x squared minus 7x plus 5. That means when I use long division, I need to get a 0 for my answer. It divides evenly. I'm thinking about how many times will x divide into 3x cubed. So you're thinking about multiplication backwards. I get 3x squared times this x is 3x cubed. And 3x squared times negative 1 is negative 3x squared. Then we want to subtract from these terms. This goes away, and this adds up to be 2x squared, and then we're going to bring down the negative 7x. Go back to the original idea. How many times will this x go into 2x squared? Evenly. So that would be 2x, and 2x times x is 2x squared, and 2x times negative 1 is negative 2x. And we're back to the same routine. We want to subtract both terms in this next step. That would go away. And negative 7 plus 2 is negative 5x. And we're going to bring down the plus 5. And then negative 5 times this x is negative 5x. And negative 5 times negative 1 is positive 5. And we got that. So up here you can see that 3x squared plus 2x minus 5 can be factored as 3x plus 5 times x minus 1, and you can use distributive property twice to see that that works out. So our factors are 3x plus 5, x minus 1 from this factor, and then this factor, which also divided evenly. So 3x plus 5 times x minus 1, quantity squared. You did a great job.